Hello, everyone. Welcome to section 3.1. The section is on quadratic functions and models. It is the first section in chapter 3, which is on polynomials and rational functions in general. But for now, let's focus on quadratic functions. So we've already kind of talked about them a little bit. So recall a quadratic function is a polynomial of degree 2. Yeah. Degree 2. So, for example, they'll be of the form, so we have our function f of x is a naught a constant plus a1 x plus a2 x squared. So a naught, a1, and a2 are all numbers of some sort. So, for example, something might look like f of x equals, like 2x squared minus 3x plus 4, for example. And so if you look at this here, this is our a2, negative 3 is our a1, and 4 is a naught in this case. All right, pretty standard stuff. I think we've all seen this before. So I'm going to introduce something a little bit different about quadratic functions, and that's standard form. So the standard form for a quadratic function looks like this. So you've got f of x, and then you're going to have some number a, and you've got x minus h, another number, squared, plus k, another number. All right, so for example, a quadratic in the standard form might look something like 2 times x minus 3 squared plus 1, for example. So here a is 2, h is 3, and k is 1. And we'll see why the standard form is useful in a minute. But first, how do we find it? So how to find? And the answer is completing the square. So some of you are probably familiar with completing the square. It's a common factoring technique. I'm going to go over it briefly here because it's a little bit different in this context, but the idea is the same. So completing the square. So the formula that's going to be useful for this is that if you have x squared plus bx plus b over 2 squared, that's going to be x plus b over 2 all squared. This is going to be a useful tool for what we're going to be doing. And the reason that this is true, you can do this with the perfect squares factoring formula. Okay, so let's look at an example of completing the square in our context. So let's say we're starting with a quadratic function, and maybe it looks like 3x squared minus 12x plus 6. And so what I'm going to be doing first is I'm going to be looking at the stuff in parentheses. So I just put parentheses around there to emphasize that I'm looking at this first. And what we're going to do is you're going to want to take whatever number is in front of x squared, so in this case a 3, and you're going to want to pull it out of both terms. And so this will be 3 times x squared minus, and then 12 divided by 3 is 4x plus 6. All right, and you can see that if you take the 3 here and you go back into the parentheses like this, you'll get back out the thing we started with. So pull the number in front of the x squared out. Next, what you're going to do is you're going to add in this important bit right here, the b over 2 squared. And we'll see why in a minute. So if we add in b over 2 squared, so b, in this case, we're looking at it in this context here. So the b is going to be -4. We have -4 over 2 squared plus 6. And then because we added something in, we have to take something away to make sure that the equals, that it stays equal. So we're going to subtract out the leading coefficient. So circle it in blue. We're going to subtract out 3 times this thing here. So what we'll get is 3 -4 over 2 squared. And so the reason why it's 3 times that is because if you were to take this 3 and factor it back into the parentheses, you'll find that this yellow thing circled here and this red thing circled here will cancel out. Okay. So a little complicated, but this is the worst it gets. So now what we can do is remember our formula up there. It said that we have something like this. We can write it as a perfect square, right? So we made it so that we can do this exact thing inside the parentheses here. So this becomes x plus, sorry, not plus, -4 over 2 squared plus 6 minus 3 times -4 over 2 squared. All right, it's already looking a little bit better. So let's just do some simplifications. So this becomes -2 squared plus 6 minus, and then this becomes 3 times -2 squared. And we get same thing here. Oops. There we go. Plus 6 minus 3, and then -2 squared is 4. And so now we get 3x minus 2 squared plus 6 minus 12. And then lastly, we'll combine the 6 and the 12, and we will get -6. And that is standard form. Excellent. Okay, so that was a lot of nitpicky work, and it probably doesn't seem too easy to do at all. So why do we care? Why are we doing this? Why do we care? The answer is you can use the standard form to find the vertex really, really easily. And the vertex will be nice for modeling, as we'll see in just a minute. So let's say I have something in standard form. So we've got our a, our x minus h plus k, like that. So we've got something in standard form. And depending on the sign of a, so depending on whether a is positive or negative, you'll have one of 2 cases. So you either get the case where you have your parabola facing up, or you have a parabola facing down. In both cases, the vertex here is given by hk. That's the coordinate of the vertex. The same h and k that are right here. See, so if you write it in standard form, you can immediately say, the vertex is h comma k. So in this case here, we've got -2, -6. The vertex here will be 2, comma, and then because it's plus k, this could be -6. Okay. And the reason we care about the vertex is because this is a maximum and this is a minimum. And that's very useful for when we're trying to do like optimization problems, as we will see shortly. So let me write out some general rules that I've said verbally. So if a is greater than 0, so if it's positive, the vertex is a minimum. And the minimum value is k. Similarly, if a is less than 0, so if it's negative, the vertex is a max. And the max value is k again. So you can use these ideas and you can actually derive a formula for where the vertex will always be using completing the square. So formula. Vertex of a parabola where it's, f of x, and instead of writing it in standard form, we're just going to write it this way. A squared plus bx plus c is given by the formula. So x equals negative b over 2a. So if you have a parabola written in this way, then you know that the vertex is always going to be at x equals negative b over 2a. And so the vertex coordinates are, and it's going to be negative b over 2a, and then whatever the function spits out at that point. So we have this formula. Why did we go through all the work of doing the completing the square stuff? Why not just always use the formula? Well, it's still good to know about completing the square. It's still good to know where this formula comes from. And completing the square can be useful in other contexts and in other classes. So it's good for you to see it here and now. And with this formula, the same sort of rules hold. So if a is positive, we have a minimum at that point. And the minimum value is f of negative b over 2a. And then similarly, if a is negative, we have a maximum. All right. So we've talked about standard form, talked about finding the vertex. We've talked about where it is a max and when it's a min. So now let's move on, shift gears a bit, and let's talk about modeling with quadratic equations. So far, we've mostly talked about modeling with linear functions, but now we can start talking about more complex processes that require quadratics to model. And in fact, we could talk about optimization problems. So let's look at an example. A vineyard has used this data on its grape production to model the number of pounds of grapes produced we'll call that A, from n vines. And so that model is A of n, A of n equals n times 10 minus 0.01 n. So the question, my first question is, how many vines should be planted for maximum yield? So the key word here is maximum. So since we're looking for a maximum, we want to find the vertex. Okay, so method one, there we go. Let's find it using completing the square. It's good practice. So A(n) was this, right? We're going to just do the same thing that we did last time. So first I'm going to write it, I'm going to expand it. So I'm going to FOIL the n in there, and we're going to get negative 0.01 n squared minus, or sorry, plus 10n. And now the first step was to take this thing that's out in front and pull it out. So we get 0.01 n squared, and then if you divide 10 by negative 0.01, you're going to get negative 1,000 n. Okay, and you can take that number, distribute it back in, and you'll see that it does indeed work out. Now we need to add and subtract our thing. I'm actually going to move this over here. So we get minus 1,000 n. And remember, we want to do, with respect to this polynomial right here, negative b over 2 squared. So we're going to do plus, and then negative 1,000, negative 1,000 is just 1,000 over 2 squared. And then the front number, so negative minus negative 0.01 times 1,000 over 2 squared. All right, and now it's just simplifying from here. So we get the same thing out here, n squared minus, oh, sorry, I almost forgot, crucial step. Using our formula, our perfect square formula, you'll find that this becomes n minus 1,000 over 2, all squared. And then the same thing over here. Okay, now it's simplification. So, and this is 500. And then this becomes plus, minus is plus 0.01. And then this is 500 squared. And minus 500 plus, and then 500 squared is going to be 25 and then 4 zeros behind it. And then simplifying some more, we get, so when you do this multiplication, you'll get 2,500. And this is standard form. And so the vertex is going to be, remember, the formula is, let me write it down for you. So it's going to be f of x equals a, and then it's x minus h squared plus k. It's a little tricky to remember where the plus is and where the minus is. But the vertex here will be 500, and then k is 2,500. All right. So that means since our this was our n and this was our f of n, max yield is when you plant 500 vines. And it is indeed a max. So it's max because a is negative 0.01, which is a negative number. Okay. So our max yield is at 500 vines. And when you plant 500 vines, in fact, you know that you're going to produce 2,500 pounds of grapes, according to the model. Okay, so that was completing the square. I imagine most of you will prefer second method, which is to use the formula. So remember, we started off with an, and then we distributed it in. So I'm just going to write out that form. So we have n squared plus 10n, because now we know that the max is going to occur when x equals negative b over 2a. And B here is 10, so we get negative 10 over 2, and then A is negative 0.01. And then if you simplify out this division, you get 500. Wow. And again, since A is negative, we have a max. And so max yield is at 500 vines. Okay. So the formula, much faster, much easier. Completing the square is still good to know, though, to keep in the back of your mind. So I could ask a different question that does not have to do with maxes or mins. So maybe ask a question like, how many plants is too much? To be more precise, like how many would we have to plant to get 0 grapes? Right? We could plant 0 plants, but according to the model, there's another point where you planted too many plants and you end up back with 0 grapes again. It's not realistic per se. I mean, you plant any number of grapevines, you're probably going to get at least 1 grape, but we're only dealing with the model, so we're just looking at the parabola. So we're asking, where is A of n equal to 0? Okay, so to write that in symbols, remember n was n times 10 minus 0.01 n, like that. And so it's already factored for us, which is really nice. So we can just use the zero product property. So an is 0 when n is 0, which makes sense. That's when you haven't planted any vines, so you're going to get 0 grapes. And the other one is 10 minus 0.01 n equals 0. And then if we subtract 10 from both sides, we get this. And then when we divide both sides, we get n equals 1,000. So we also see that we get no grapes at 1,000 vines. So the model says that if we planted 1,000 vines, we're going to get no grapes. So the model might not be completely accurate, but all we have to work with is the model in this class, so that is what we will do. All right, this was a lot of material. So to recap, we talked about the standard form of parabola. We used completing the square to find it, and then we talked about how we can use that to find the vertex of parabolas, in addition to finding a formula for the vertex of parabolas. And then we use that to decipher and understand quadratic models of things so we can answer specific questions. All right. A lot went on in this video, but once you get your hands dirty and start working with the math yourself, I think it'll start clicking a bit better. All right. So go forth, do the homework. And of course, if you have any questions, I will be in office hours.